This is a lesson on the mathematical model of simple harmonic motion on a calculus-based engineering physics course. In another lesson, I talked about how simple harmonic motion is ubiquitous throughout the cosmos. We have particles on waves. This is a sound wave. We have guitars, slinkies. We have uniform circular motion. We have actual things moving in circles. We have something that looks like circular motion, a mass on a spring moving up and down. We have a pendulum. Those are simple harmonic oscillators. And we have a quantum harmonic oscillator for when two small objects are connected to one another and vibrate, creating energy levels. We can see that here. So simple harmonic motion is one of the basic conceptual and mathematical models used in physics. I am going to remind us from pre-calculus about sine and cosine functions, not just trigonometry, but trigonometric functions that we graph, right, as a function of x, or as we're moving forward, this is going to be a function of time, and the variable that we're going to get out is a position with respect to time. We have objects, real material that is vibrating in space, and it will have a position. Okay, and so sine and cosine are cyclical, right? They repeat on regular intervals called periods. And so we can a priori know that we're going to use sine and cosine functions in order to model simple harmonic motion. As you move forward into calculus and you look at differential equations, you may even be in a differential equations course. This will be a second order differential equation created by force analysis. We have force on one side and the second derivative of position on the other. Force will typically be a function of position. So that's where our second order comes from. We can also do torque. Torque is also a function of theta, and then we get I times alpha, and we know alpha is the second derivative of theta with respect to time. So we have second order differential equations here. So I have a slide on that in a little bit. Overall, I wanted to remind us how to model with sine and cosine functions. So again, this is pre-calculus material. You may remember how to shift and stretch functions on a coordinate plane, on coordinate axes. If we want to scale it, there's a scaling factor. We're going to recognize this as the amplitude for our motion, A. B is related to the period of the function, how frequently it repeats. All right, and that is in here in our sine or cosine function, that B term. C is related to a shift. We call this a phase shift, and it's a shift in the x direction. It may shift left or right on the coordinate plane. That's this term here. Notice that this by standard convention is a negative sign in here. So if we have a positive shift, if we shift to the right, a positive shift, we'll have a minus sign in here, and if we shift to the left, we'll end up with a positive sign, which this may become an issue when we're looking at phase shifts and signs, but I'm going to give you a tip of how to figure out whether this is a plus or a minus sign. And then also there's this D factor. This D factor on the end shifts it up or down. So you may shift up or down on the coordinate axes. So this is a reminder of how to use sine and cosine functions from pre-calculus in order to model sinusoidal behavior. When we look at simple harmonic motion, we simplify this down, and this is most texts start with a cosine function. I am going to tell you that you can use a sine or a cosine. A sine or a cosine will work, especially if you choose the right phase angle, right? Because cosine theta is just a shift of sine theta plus a pi over 2, right? They're shifted 90 degrees from one another, a factor of a pi over 2. So a sine or a cosine could work in here, but by just tradition and convention, we choose a cosine. Okay. Again, A is the amplitude. The period, omega, is how frequently motion repeats. Remember, omega is in radians per second. We could measure the frequency in hertz and relate it to the omega, or we could have t, which is the period, in seconds. Okay, so that's where the omega goes in the equation. Phi here, I call this Greek letter phi. Some people call it phi. I'm fine either way. It's the phase shift, and it's in there if and only if. So if you're in math, you recognize the if and only if acronym here. The object is not at maximum displacement at t equals 0. So often we will use this to represent a mass on a spring. All right. And if you did this in lab, you pull a mass on a spring out from its equilibrium position. And notice that if we do that, we at time equals 0, we have cosine 0, or cosine 0, which is 1, and so we get the amplitude. So at that position, x of 0 equals the amplitude, which is true for if you start time when you pull it out to the maximum displacement, the amplitude. You will have a phase shift if t equals 0 does not happen at that point in time. You could start t equals 0. You can start a clock anytime in simple harmonic motion at any point in that motion. So you could have some random phase shift depending on when t equals 0. And what you need to do to figure that out is you look at the initial or boundary conditions of the motion. They may say like x of time 0 equals 9.2 centimeters. Okay, so then when you go to plug in t equals 0 here, and then you know what this is, you'd know what the amplitude is, and you can figure out the phase angle from there. Okay, so phase angle depends on the initial position, and you'd have to do some math on this with the trig function in order to figure out what the phase angle is. There may be some shift of the midline up or down. Often you might see this where like if you have a spring that is attached to the ceiling, and like they say maybe the ceiling equals 0, and so the equilibrium position is some distance below that. That would be that d on the end of the equation, and it would be just a shift, a vertical shift on the graph. For most intents and purposes, physicists like to keep this easy, and we will have no plus d on the end. We will define the equilibrium position here, and so we wouldn't have to take into account any d factor. Okay, so that is true for simple harmonic motion in 1D. I wanted to present a quick slide here about what phase angles look like, just to remind you. I know in pre-calculus there's a lot going on, and maybe this was a little detail that might not have come together 100% for you while you were there. This is a sine function. You all see the blue here, or at least you can see that this function here starts at 0. We know sine 0 equals 0. We know it starts here. It peaks at 90 degrees, goes to 0 at 180, and so forth. It comes back to a cycle. Okay. I can look at a phase shift. If I look at this green function here, all right, I have a minus pi, so I have a plus 180 degrees, right? So I said if there's a minus in here, that means we're shifting to the right. Do you all see how I've taken this blue function, I've taken this whole blue function, and I've shifted to the right 180 degrees, and I get the green function. And so that's how I think about phase angles, is a shift on the graph. I'm going to just take that whole graph and shift it to the left or shift it to the right. For the red function here, you can see it says pi over 4, which is what, 45 degrees. I know pi over 2 is 90, so pi over 4 has to be half that. So that's a 45-degree shift. And I can see that instead of starting at 0, I'm going to have sine of 0 minus pi over 4, right? So that gives me my initial start here at pi over 4. And so there's the original value, whatever the sine of negative pi over 4 is. I probably should know it, negative 1 over root 2 maybe. So I've taken this blue graph and shifted it just 45 degrees over, and then I get this red graph. Okay, so again, that's how I think about phase angles here. Is we call it a phase shift, all right, or a phase angle. Those two things are synonymous to me. They mean the same thing, phase shift and phase angle. Okay, so as we move forward, we're looking at the model for simple harmonic motion 1D. I showed you the position. There's all the values for the position. If we want to find instantaneous velocity or acceleration, we can easily do that. We're just going to take a derivative with respect to time of the position, and once we get the velocity, we can take the derivative with respect to time to get the acceleration. Okay, so again, we're gonna, or not again, I guess, I haven't mentioned this. We have the chain rule going on. If we take the derivative of cosine, we're going to get negative sine. But then we also need to take the derivative of what's inside here with respect to time. And so we're going to get a factor of omega. A factor of omega comes outside, and so we have negative omega A. I'm going to point out to you here, books make this look like an equation, but you can look at this and say, oh, well, whatever term is out front, that's going to be the maximum value, right? I can do that with position. That'll be the maximum value. The maximum velocity is going to be omega times the amplitude, and the maximum acceleration is going to be omega squared times A. Disregard the negative because it's a vector, right? These are technically vector quantities. I didn't indicate that. These are technically vector quantities. So as an object moves back and forth, let's say we have our spring, mass on a spring again. As it moves back and forth, the acceleration and velocity are going to change direction. But if we want to look at the maximum values of those, I do omega A or omega squared A. Okay, so that gives us some ground to be able to do some mathematical modeling for our simple harmonic motion. Problem that I picked out as an example is a position function from the graph. It says the graph shows the position of an object in simple harmonic motion as a function of time. So you can see time down on this axis and position on this axis. So we have position as a function of time. What function describes the position of the object as a function of time? So we need to fill in, basically what they're asking us to do is fill in all the terms in here. What is the A term? What is the omega term? What is the phi term? T is our variable as a function of time, so we're going to leave that just as a variable. And so we need to figure out the other terms. You may be quick on this. The amplitude of the motion is given by how far it is away from the time axis here. Notice that there's symmetry about this. We're going to have a positive amplitude at some points in time, and we're going to have a negative amplitude at other points in time. But the value of the amplitude here we're going to see is 1.4 meters. Omega I would find by 2 pi times the frequency, or I could do 2 pi over the period. We can see on here, because we're given time, it might be easier to find the period. I'm going to locate one cycle of motion. So up, down, and then up again. Okay, so from this point to this point is one cycle. One cycle. You could do that again here. Here's another cycle. There's another cycle. Okay, and we can see that one cycle is 2 seconds long. So we're going to see that T equals 2 seconds. The period time, big T time, is 2 seconds. So if I want to find the omega, I'm going to have 2 pi over 2, which is pi seconds. Oh, sorry, pi radians per second, right? It's covering 2 pi radians in T seconds. So our units on angular frequency is radians per second. This can creep some people out. It's disarming to see that there's some sort of radians going on, but the object is not in circular motion. The radians here represent where in a cycle it is. So we're going to keep our idea from circular motion about being in a cycle, all right? But when we think about cycle, we're going to think where we are in For example, we might have a mass on a spring oscillating back and forth. It's not moving in a circle, but it is cycling back and forth and back and forth. All right. So depending on where it is in that cycle, we're going to have so much of a cycle in radians go by. I'm hoping that's making sense to you. The last thing we need to figure out here is the phase angle phi. Okay, and so I picked this example. This is going to be an easy example to find the phi angle. You may be given different information in a different problem to find phi, but this will be the general technique that you do. We'll get an easy answer here, but you'll have some tools to be able to do this later. I'm going to get rid of some of this information on here so we can see the graph better. So there's our graph again. Okay. And in our initial position, so this is what I said. Where is it initially? If I say x of 0, where is it initially? Well, I look at this graph and I can see that the initial position is 0. Okay, so I'm going to plug that information into my equation. X of 0, so x of 0 is 0. That equals 1.4 cosine of pi times 0 plus phi. Do you all see how I did that? I have t equals 0. I have position equals 0. X of 0 equals 0. I have my amplitude in here. I have my omega in here. The only thing I don't know in this equation is phi. Okay, so let's do some algebra. If it's equal to 0, I'm going to notice that this constant term out front doesn't matter. So I'll get cosine. 0 equals cosine of pi times 0 is 0, so I just get cosine phi here. Well, I can do this. Phi will equal the inverse cosine of 0. The arc cosine is 0. And I know there's two answers in 360 degrees. Of course, there's going to be positive 90 degrees, right? When I look at the unit circle, right? I'm going to have no x component here, and I'm going to have no x component here. So I know that I'm going to have another answer of negative pi over 2, or you could call it 3 pi over 2. Typically, we do a negative pi over 2, an angle between negative 90 and 90, something less than 90 degrees in absolute value. So there's a possible two answers here, if you remember that from trig. That is totally in line with what trig tells us. There should be two angles that have a cosine of 0. All right, so which one is it? Which one is it here? Well, I went and what the best thing for you to do in this situation is not guess. Do not guess at what it is, and hopefully you're just entering an answer into the computer and you'll just guess the other sign next. But how do you know no? Okay. So remember what I was saying. We have our two possible answers here. We have x of t equal 1.4 cosine pi t minus pi over 2. So that'll be our original, right? If I have a positive value, and I know this positive here throws it off. By convention, it should be a minus sign in here, all right? Or our other answer could possibly 1.4 cosine pi t plus pi over 2. Those are two different functions. Those are two different functions on a graph. What I want to do for you is show you the two different graphs here. Okay, so I did this problem a little bit earlier, and this is my work from a little bit earlier. Up here, this is this graph up here is the cosine 1.4 cosine pi times t plus pi over 2. This is the plus one. And this is 1.4 cosine pi t minus pi over 2. I just graphed them. Okay, so this means that was shifted 90 degrees to the 90 degrees to the left, which makes sense. It's not shown here. I didn't put it on here, but here's cosine. And you can see that this whole entire graph from cosine was shifted to the left 90 degrees. As opposed to down here, it's here's cosine. It usually starts here. It's been shifted to the right 90 degrees. Okay. So when I'm looking, I just matched up the graphs. When I'm looking at it, I see that I want it to start at 0. Both of these start at 0, which is what the solution told me. But when I look at the graph, I want it to peak next, positively up here, not negatively. And so I know my equation is going to be 1.4 cosine with a minus pi over 2. So that's why I was saying it's a little bit confusing when they put this positive sign up here. Be careful when you're finding phase angles because it does affect that value in here. So we're going to note that this is not the equation. So my position function as with respect to time is going to be this equation here. Okay, so I thought that was a good example of reminding you about the positive and negative answers and figuring out how to select the right phase angle in this situation. I am going to point out that the simplest way to represent this function would be with just a sine pi t. Then I wouldn't even have a phase angle. This is a completely legitimate, correct answer as well. Both of these answers are correct. Both of them, right? So you may be forced to answer it with respect to a cosine, but it could be that you just notice that it's a sine and just leave it there. So the next thing that I wanted to talk about with you all is the mathematical model for a mass on a spring. Okay, we're going to keep the same equation. What I derive for the position as a 1D position as a function of time for simple harmonic oscillators is the true for that mass on the spring. You saw me using that example. Again, oh, here we go. Again, here are your variables in there. We want the angle in radians. We're not going to use degrees in here. So when you're doing calculations and you're trying to find cosine of something with simple harmonic motion, make sure that your calculator is in radians. We need radians in there. Okay. Again, we can take the derivative and the second derivative to get the velocity and the acceleration. All right. And I put these graphs over here. You can see how at different points, right, when it goes through like the equilibrium position, see it's at the equilibrium position here. When it's at the equilibrium position, and we'll study this a little bit more with energy, it'll reach a maximum velocity. Equilibrium position, another maximum velocity. Equilibrium position, another maximum velocity. So when it goes through the center of the motion, it's going to be at maximum velocity. When it stops here, that's where it stops. We can see it stops here, here. That's where it's stopping. That's where it experiences the maximum force and the maximum acceleration. Okay, so those things don't happen at the same time. Maximum velocity is when there's zero position. Maximum acceleration is when there's maximum displacement. Again, we can read these formulae off of our graph. Like this will be the maximum value. This will be the maximum value. The negative sign here represents a vector quantity, right? It'll be the opposite of what the displacement is. I wanted to show you how to derive the frequency of motion for a mass on a spring. It's a very easy equation, but I wanted to do this just laying down foundation for looking at wave motion and figuring out differential equations for wave motion. We're going to start with a force analysis here, and I put that on the other slide that we had earlier. MA, F equals MA, good old Newton said that. The force, if we have a mass on a spring, we know the force on a mass of the spring. If we just look at the magnitude, or even a vector, we're going to have K times delta X. Yeah. Some people just put an X here, which is fine, as long as we're starting at equilibrium position, right? When we're doing this, we're going to start at an equilibrium position. Y equals 0, so we pull it out and some distance x. And this will be a function of time. We know that from previous, right? This is a function of time. We're going to have mass times acceleration. Acceleration is also a function of time. Okay. We know the solution, right? This is sort of what it'll look like. K, and if you're into differential equations, this is what it'll look like. D squared x of t over dt. We wave our hands and guess the answer, but this is how I started the whole lesson today, is that the solution will be a sine, a cosine, or an exponential, right? When I take a second derivative of any of those, I get the same function back. And it'll look like this, right? If I put in what I know about x of t, I'm going to have k, a cosine omega t plus phi equals m times negative a omega squared cos omega t plus phi. Just plug that stuff in there, okay? I know, how do I get rid of this negative sign? There's a negative sign here. When we look at spring force, if I displace it in this direction, the force has to be in the other direction. So I need a negative sign here, negative sign here, negative sign here. So that helps with my negative signs. And also, I'm going to notice that A is here, cosine omega t is here, and I'm going to get this, when I simplify this, you might be able to see it, I get k equals m omega squared. That's what's left over when I cancel things out. If I solve for the angular frequency, right, and that's why I was looking for the frequency of motion, I'm going to get k over m square rooted. That will be the angular frequency. So if I know the k and I know the m, if I know the spring constant here and the mass of the whatever is on the end of it, I have a box, I can find the angular frequency. What I'm going to note to you here, and is a common misconception, is that this depends on amplitude. Notice that the amplitude cancels. It cancels on both sides. The position depends on amplitude, but also the acceleration is dependent upon the amplitude. And because they're both linearly dependent on the amplitude, it cancels. When you pull it out farther, it's going to move faster, all right? And it's going to kind of cancel out the motion. It's going to move back and forth just as fast, which is interesting. It's not amplitude dependent. So watch out for any misconceptions or questions that might have you answer that. Is, does it depend on amplitude? No, it does not depend on amplitude. It's just the spring constant and the mass. That's the only thing that determines the angular frequency. We saw this in lab. If you've done this in lab, this needs to be small x, a small x. We do not want to damage our spring. We don't want to break it, right? So we're staying within small motion where we can do some, where we're not losing energy due to deforming the spring, okay? Or breaking the spring, I guess I'll say. Okay, so I have our final example here, simple harmonic oscillator equation of motion. Okay, so we have a mass on a spring. A block of mass 4 kilograms is attached to the end of a spring and set into motion such that the equation for the position is given by this. So we're given the position equation. Before we had to derive it, here we're given it. And it asks us a series of questions, and we're going to have to read this equation in order to get information out of it in order to answer the questions. The first one might be easy. What is the amplitude of motion? Well, when I look at the equation, the amplitude is the term out front. I can see that the amplitude of the motion is going to be 3.2 centimeters. Okay, so that was easy, 3.2 centimeters. Okay, let's keep moving. What is the period of motion? Well, I know the period of motion is related to the omega, and the omega is in the cosine term, right before the t. So here's the t. So this term here, all of this is going to be omega. Omega equals 15 pi radians per second. So if I want to solve for the period, I'll go 2 pi divided by 15 pi. And so I get 2/15 seconds. I'm not sure what that is. I guess I do know what it is. I calculated it to be 4.7 milliseconds. So it's moving fast, moving back and forth pretty fast. That's its period, is 4.7 milliseconds. Okay. So there's omega. There's the period. What's the period of motion? What's the spring constant? Okay. We're going to have to do a little bit more work here. So the spring constant does not come up in the equation, but remember we just derived how to relate the omega to the spring constant. So I know omega equals the square root of k over m. So if I want to solve for k, I'm going to get m omega squared. If you're all okay with that algebra, I did really quick. The mass they tell us is 4 kilograms. The omega squared is 15 pi, quantity squared. And when you run this through a calculator, I did this a little bit earlier for us, you get 8,882.63. And remember, the units, standard units on K is newtons per meter. So that's our K value there. Pretty strong spring. Really strong spring. The other day we used a spring in class for lab. It was 1.7 newtons per meter. That was a little spring. So this is a really strong spring. And we're noticing that's true. It has a really small period. It's going to move back and forth really, really fast on that 4 kilogram mass. What is the phase angle of motion? Okay, let's look at the phase angle. I'm seeing, right, if we look at this equation, and I don't have phi's, the standard phi here. I had another form. Phi, this will be our phi value. We just look at that and say phi equals pi over 2 radians. Is this positive or negative? Again, and this is where it can get confusing, there's a plus here and there's a plus here. So our standard form for simple harmonic oscillators or simple harmonic motion is a plus sign here. This is a plus sign here. So I'm just going to say that the phase angle is positive. Okay. E, what is the object's location, velocity, and acceleration at 3 seconds? Okay, let's do this. X, they want x of 3. It's just like evaluate the position at 3 seconds. So I'm just going to plug in 3 seconds. I get 3.2 times cosine of 15 pi times 3 plus pi over 2. Okay. 15 times 3 is 45, so I get 3.2, the cosine of 45 pi plus pi over 2. I'm going to do this a little bit different, quick way to think about it. This is how a physicist might think about it. If I divide 45 pi into 44 pi and a pi, I get 44 pi, which I'm going to remind you is 11 revolutions, if you're okay with that. Right? 2 pi is 1 revolution. If I have 44 pi, I have 11 revolutions. And then I have this 3 pi over 2 term. So what I'm noticing, right, I can get rid of this whole revolutions, okay, because they're, what do they call it? I had the term earlier, coterminal. These are coterminal, right? 45 pi plus pi over 2 is the same as 3 pi over 2. Coterminal. And basically that just means like on a unit circle, it's down here at this position, 3 pi over 2. I could go around 11 times and end up at 3 pi over 2, or just think about just being at 3 pi over 2. Well, I know cosine 3 pi over 2. Cosine 3 pi over 2 is the same as pi over 2, which is 0. So I know the position at time 3 equals 0. Okay. If I look at the velocity, what's the object's velocity? The velocity at 3 seconds. Well, I'm just going to copy this stuff down. I'm going to have a negative 3.2 is the amplitude, omega 15 pi, sine of 15 pi times 3 plus pi over 2. Let's do the same trick. I get negative 3.2 times 15 pi times sine of 3 pi over 2, right? This term is going to be the same as this term. So we know it's just 3 pi over 2. I know sine of 3 pi over 2, well, that's a -1. So if I want the velocity of 3 seconds, I'm going to get negative 3.2 times 15 pi times -1. And so I'm going to get a positive value. When I run that through, I actually get 150.8 meters per second. Positive. Acceleration is also a cosine term. I can do the same thing that I did, times 15 pi squared technically, but I'm going to get cosine 3 pi over 2 here, and so we know that the acceleration is going to be the same as the position, which is 0. Okay, and it seems as though, I didn't really say this, but if I'm at 3 pi over 2, if I'm at position 0, acceleration 0, this to me, I'm noticing is V max. I'm at the position at t equals 3, I'm at equilibrium position right here. Okay, I'm moving in the positive direction. Right, that's what my Vmax says. I end up with a positive sign, so I'm moving in the positive direction. There's no displacement and there's no spring force. There's no acceleration because I'm at the equilibrium position. So hopefully this helps you through whatever problems you need to solve, and also setting a good foundation conceptually for how to model simple harmonic motion with trig functions.